Assalamu alaikum. Good evening, everyone. Welcome to our Geomechanics webinar. My name is Ahmed, and I'll be your host for today's session. It's my pleasure to be with you today. Our speaker for this session is Dr. Mahmoud Youssef, senior geoscientist with more than 15 years of experience in the oil and gas industry, covering exploration and production across several regions. He holds a BSc in geology, a master's degree, and recently earned his PhD in 2021. Dr. Mahmoud has participated in major projects in Egypt, Saudi Arabia, Sudan, and Algeria, working with both international and joint venture companies. Before we wrap up, in the last 15 minutes of the session, we will share a link to the attendance form. Please make sure to fill it out to receive your webinar certificate. Kindly note that the form will close right after the webinar ends. Mr. Mohammed, the mic is yours. Dr. Mahmoud, can you hear me?
Yes, Mr. Amr, I hear you very well. Good evening, everyone. We are here today for a webinar about technical reservoir geomechanics. I will share my screen. A technical webinar on reservoir geomechanics. In our presentation, we will explore how rock mechanics principles apply to real-world reservoir challenge. Geomechanics helps us to understand the rock behavior under stress, how pore pressure interact with the stresses, and how this affected drilling, completion, production. By the end of this webinar, you should have a clear picture of how geomechanics modeling contributes to safer, more efficient field development. And let's start by exploring why geomechanics is important for geoscientists and for the engineer. First, geomechanics apply fundamental rule in every stage of the drilling and reservoir engineer. It helps predict control issues like compaction, subsidence, and production-induced faulting. During drilling, geomechanics support well bore stability, analyzes the mud weight to choose the safe mud window, and the drilling direction plan. Also inform completion design, minimize the sand production, and maintain long-term well integrity. Beyond the drilling, geomechanics is also important in reservoir characterization and geophysical interpretation and geological. It aids to predicting the pore pressure through the velocity of the sonic and also to detect the mud weight used for drilling, understanding the shear velocity, fault seal integrity, and hydrocarbon migration and reservoir compartmentalization. It's very important to understanding also the in situ stress on the pore pressure condition. Also, it's used for fault seal integrity. This is insight are essential for identifying compartmentalization, and we can improve our reservoir model and reduce the uncertainty. This is for conventional reservoir. For unconventional reservoir, geomechanics is indispensable. Shale, gas, tight oil, and tight gas formation, ultra low permeability, meaning production depend on induced and natural fracture. It's not normal like conventional reservoir. Understanding how this stress and the mechanical properties control fracture and propagation also allow in our engineer or scientist to optimize well placement and the multi-stage hydraulic fracture design. Also, geomechanical model also help to simulate production and managing fracture interaction to enhance recovery efficiency. Also, it is very important to know from the geomechanics, not all unconventional resource can be hydraulic fracking, and we discuss this in detail in our workshop. Maybe the decision is to didn't to go to make hydraulic fracking in some interval of the unconventional resources due to the stresses problem, or we can discuss this in detail, inshallah. Discuss how geomechanics evolved through the life of the field. Is geomechanics also affects pre-drilling and during drilling, or it's much wider? Yes, geomechanic consideration spans the entire life of the cycle of the field, not only pre-drilling or during drilling, it's also after drilling until development and finally abandonment. As well-calibrated geomechanical model enable better well planning, improve safety margin, and allow and lowering overall cost. It support early decision of well trajectory, detecting casing design, and choose the best one. Production strategy. As a field mature, continuous update of the model based on real-time data ensures the long-term stability and reservoir management. This field-wide ensures sustainability through the asset of the life of the field. It's important for all of us during from the exploration phase until abandonment phase. Geomechanics considered Geomechanics principal stress represent the maximum and the minimum normal stresses. They are very typically categorized as the vertical stress and the maximum horizontal stress and the minimum horizontal stress. Knowing their magnitude and orientation is critical for predicting fracture direction, well bore, breakout. The three measure is SCV, which is representing the overburden, SH maximum, minimum horizontal stress, SH minimum can be detected by the image. We can detect the orientation and the magnitude of it. Additional component for geomechanical model is the pore pressure, can estimated by different method like DXC or velocity from the seismic or also the well logs. UCS is a rock strength. It can be estimated from the well logging. And also the fracture can be measured by the fault, fault fracture and faults from logs and seismic and so on. Principal stress is representing the maximum and the minimum normal stresses. Is characterized the vertical stress when the SV is higher. It means that the normal stress regime. Normal stress regime is meaning normal faults. Minimum horizontal stress and the maximum horizontal stress. SH maximum is the largest one component of the minimum horizontal stress. SH minimum is the smallest one. Understanding their magnitude orientation is important on stability, hydraulic fraction, and fault analysis, magnitude and direction as well. For the pore pressure is a pore fluid, pore pressure of the fluid within the pore space of the rock. It's play important role on the effective stress on the rock behavior. It depending on the pore pressure, hydrostatic pressure. Hydrostatic pressure, if your pore pressure estimation is matched with the hydrostatic, so you are normal pore pressure. Normal pore pressure, there is no problem. But in case of the pore pressure is lower or higher, this hydrostatic pressure, we're dealing with abnormal pressure. This case represented by under pressure. Under pressure, it means the pore pressure is less than the hydrostatic. Over pressure means the pore pressure is higher than the hydrostatic. Each one of them cause a lot of problem under pressure, causing losses. Maybe this is due to tectonics, due to fluid expansion, due to production. It's mandatory to, in this case, during the production to measurement or calibrate this pore pressure with MDT or RFT data. For the overpressure, this means this layer is compacted with high pressure. This means it's very near to the overburden stress, which cause a lot of problem like kick or blowout. Why pore pressure is important and how we estimate it. We estimate it as we discussed DXC. This is during drilling and also from interval velocity of the seismic. It's important like we see on the left side of the screen. This is interval velocity. Maybe we get a good indication before we run the pore pressure analysis if we get interval velocity lower due to the normal convection trend. This means the overpressure zone. Increasing the velocity over, it means the under pressure zone. It's opposite than the normal logs from the sonic. The second method is the logs. The well logs, as we see in the middle of the screen, this is logs estimated pore pressure, fracture, overburden, and also calibrated with the MDT. Now it's more easy, more simple. We have all the data set. We have everything. The interval velocity is used in case of wildcat wells or exploratory well or area that is not covered by logs. So we should depend on interval velocities, the available data. But in case of drilling or we have a lot of data, now we will going to use the well log. This is better. The pore pressure and the effective stress equal to the overburden. If the pore pressure is very high and near to the overburden or the lysostatic pressure, it's mean very important in case of trap failure. We will discuss this is in detail in our workshop. If the pore pressure is very near from the lysostatic or overburden, that means the trap is perched. Maybe we found a very good reservoir, very good trap, very good every petroleum system source, and unfortunately you didn't find hydrocarbon because all these hydrocarbons escape due to the trap failure, the cap rock integrity. This is very important to discuss. After that, in our field, just to use that to contrast reliable geomechanical model, we use data must be integrated from various sources. It's not depending on only one source. We will depend on all the sources together to get a better model. We should use well logs, core data, seismic survey, drilling parameter, laboratory test, and so on. All this data like to solve a piece of puzzle. For example, sonic and density logs is used to estimate elastic properties. Image log identifies stress indicator, and formation tests provide direct pore pressure measurement, like the RFT or MDT we used discussed before in the previous slide, which is mandatory to use it because it calibrates the pore pressure estimated from normal compaction trend. This is will be discussed in detail because it depends on the just on the experience of the field. In case of drilling exploratory wells, or in case in using logs right now, we should use MDT to calibrate this pore pressure, and also leak of test is important to calibrate the fracture gradient, which here is represent SH minimum. Going principal stresses, the best one is describing this classification is Anderson classification. It is used SV. SCV, this is the normal regime when SCV is higher than SH maximum, higher than SH minimum. In strike slip regime, SH maximum is higher than SCV, higher than SH minimum. In the first case, normal sigma 1 is SCV. For the reverse fault, SH maximum is higher than SH minimum is higher than SV. It is important to know the direction and the tectonic regime of your area before you're going to estimate this stress magnitude and orientation, because it gives a good indication about the regime you found in your area. Then start to estimate your stresses. If the stresses respect the regional tectonic of the area, so we are good. If not, you should return it back to see if this is just a stress in your area didn't respect the stress regional, or there is a problem in your estimation. By the way, we have also, as mentioned with Mr. Zubak, we found a stress map, including all the stresses of the area. I think it's good for just to start if you didn't have any data. The hydrostatic pressure is important because this is for the pore pressure. We will discuss the under pressure and the over pressure. On the normal faulting, as we say, SCV is the most higher one, and including the SCV here. It depends on the type of the regional tectonic of the area. It's more important to know because after estimation, the every stress, the magnitude, and the orientation, you should respect the tectonic of the area. If it's not respect this one, you should return it back to see what is the problem or the issue. By the way, not only this, maybe you are wrong in your estimation. Maybe there is area uh, just showing some problem in it, or you cannot see or didn't see it before. Maybe change the stress of this area. Also, for the range of stress magnitude, the variation in the pore pressure within the compartment is very important. This one because It is different in the fluid connectivity. Geological factor like faulting and lithology, external stress like seismic activity or sedimentation, or maybe microseismic activity due to the production. It's very important in estimating the pore pressure, and the compartment can be hydraulically isolated. Why I should know that? Because it's affecting the casing design of the well, sealing and fault, long distance pore pressure, which can either higher over pressure or lower under pressure. In this case, I cannot drill areas bed with the over pressure with bed with under pressure. I should now isolate every one of them with casing, or you will see kick or some losses, or at normal hydrostatic level. If you are in hydrostatic level, it's very good. There is no problem at this all. A variation of the pore pressure can affect casing also design and to avoid losses and gain. For the overpressure zone are the area where the pore pressure in geological formation is significantly higher than the normal hydrostatic pressure. As we discussed, it's mandatory to know that because this zone can be caused by process like rapid sedimentation that trap fluid, hydrocarbon generation, or tectonic movement. Overpressure zone is risk on drilling operation, and it can cause a lot of issue like blowout, like special precaution we should take it. They are also found in industrial and engineering context where they can lead to hazard from explosion of fragment impact and zone regulation of some, but it minimizes to this risk. Also, in some countries, due to the production of the well, we found some homes subsidence of the earth due to the production and the lowering the stress of this area. So we should always focus and real time updated pre and during and after the production as well. This is the range of the magnitude at depth. This is a real example from well drilled and it's already published. The risk in oil and gas exploration is the overpressure zone are major hazard. Why? Because it's caused blowout, and sometimes we see some rigs in fire, something problem like we face in Gulf of Mexico. It can lead to catastrophic event. So overpressure should be monitoring at all. Identification to the zone test identify this zone using seismic data and well log to analyze properties like acoustic impedance and the pore pressure. Also, we can calibrate this point with core data used for the UCS or something like that doing in the laboratory or RFT used in the well. As we see on the lowermost side of the well, the pore pressure is matches the RFT is matches the hydrostatic. It is the most safe zone. While in the area highlighted by the red circle, it's a high pressure zone and it's very near to the overburden. This is the most risky one. We don't like to see it because in this case we will increase the pore pressure. The pore pressure is very near to the vertical stress. Just a small increase on it will cause complete loss. After that, you get blowout, the formation fluid will out on you, and then خلاص, all is finished. For the stress measurement techniques, we have direct method and indirect method. The direct method is involved intentionally fracture, the formation to measure the minimum horizontal stress. Mini frac or micro frac is a test. It's mandatory before the hydraulic fracking as well to done just mini frac to estimate the stresses and compare it to the stresses you estimate before going to the hydraulic frac. It's just mini frac, less cost, but can save a lot of money. Leak-off test is also used to calibrate the SH minimum and extended leak-off test, which is the best one. But not all the engineer prefer the leak-off test extended because it's make a fracture or small fracture in the formation, but it gets the best way to estimate the SH minimum in this case. This measurement is important for calibration geomechanical model. Also before hydraulic fractions, it's very important on drilling operation. Remain with safe pressure limit. They provide direct and quantitative way, like theoretical stress model with field data. The data of stresses estimated is divided into two branches, static and dynamic. Static is the best one and it's used from core or laboratory test. You take the sample and apply the pressure until we reach the best result. Actually, in our case or our industry, this is not available at all time. So we depend on the dynamic stress instead of static, and calibrated with the data we have from surrounding well or wells that have this data. When the direct stress are not visible, and by the way, it's all time. Stress information can be indirectly from the image log. The best way to estimate the stresses often reveal well bore breakout and drilling induced fracture, which provide insight into the stress orientation breaks through with a minimum horizontal stress, while drilling induced fracture align with the maximum one. Should be noticed because in this case we will know the direction. It's very important when you during the hydraulic frac to estimate parallel to the minimum horizontal stress and to propagate on the direction of the maximum stress. So in this case, we should know the direction exactly to detect the pressure needed for the frac and also how this frac will affect on your bed. Also, this observation, when combined with the rock strength, like log data, estimation of the stress magnitude, and direction, such indirect methods are especially useful in mature field or where testing is limited. In case of lack of data, the stress measurement techniques, which is advanced method, it's like use acoustic anisotropy, sonic vision, or just image with 6 or 8 arm, analytic strain recovery, which called as ESR. It's high measure time depending on strain recovery with core preventing retrieved from the subsurface, providing information on the in situ stress. Different strain curve analysis, DSCI, this is laboratory techniques that measure the strain from core sample also. This is very advanced techniques, and the percentage of error at this estimation is nothing. It is the best way. If it's visible, it's okay. If not, we will all depend on the indirect method. This is a stress regime and direction of each stress with the tectonic and cross section and stereo net, just to add an image on each case, what you expect, and after that, you will compare on what you estimate. The stress regime defines the relative magnitude and the principal stress to control fault activity and the fracture orientation. For example, like a normal fault occur when vertical stress is greater than, while strike slip reverse faulting corresponded to other stress. It's minimum and horizontal stress. Regional stress regime help on aesthetic fault reactivation risk, also planning well trajectory, and design hydraulic fracture with the prevailing stress field. The effective stress principle form the foundation of reservoir geomechanics. It states that the total stress is distributed between the solid rock matrix and the pore fluid pressure. This means any change in the pore pressure due to production, injection, or depletion, in 3 cases, directly affect the rock mechanical response. Understanding the effective stress allows engineers to predict reservoir compaction, sand production, and the potential fault reactivation. It's very, very important. We will discuss it in detail on our workshop. 3 major problems we faces in our production for our companies, like potential of the fault reactivation and sand production, which cause a lot of money, especially if you're drilling on the offshore or you're drilling from the pipe. It is mandatory to study this very well because the sand production causes a lot of problem. In practical terms, managing pore pressure is a key, maintaining the reservoir and well integrity. Going directly to the elastic rock properties. Elastic moduli include Young's modulus, Poisson ratio, shear moduli, and bulk moduli. Our main elastic moduli, this is very important in our geomechanics, Young's modulus and Poisson ratio. Actually, why this is very important? Because this is in measure the stiffness of the rock. Which one will be brittle? Which one will be ductile? Which one of them is suitable for fracture? And detect the best pressure needed for the frac any of this layer. So it's very important. This parameter is widely depending on the lithology and the pore pressure structure. A higher Young's modulus indicates stiff rock, while the low Poisson ratio implement limit lateral deformation. Accurate estimation of this parameter from logs or core test is essential for the well pore stability, hydraulic fracture design, and compaction studies. They define how stress redistribute during drilling and production. So it's very important to know. Bulk modulus is dealing with the deformation in the volume. Shear moduli is elastic contain realistic shear strain, shear stress. Young's modulus, it is the most one we should know and estimate it correctly because it will affect a lot. We will give two examples from this wrong Young's modulus, how to lead us to spend a lot of money and lose the will. We will discuss this in detail, I think, in 3 or 4 days. We will discuss in detail with a real example, with a real problem we face. Some geomechanical analysis application. It is very important throughout the life cycle of the oil. It's not only during the drilling, as we discussed before. Exploration, production, minimize risk, optimizing operation. We have several application. We just for the time drilling application divided into three: drilling and reservoir application. Drilling application like pore pressure and overpressure is used to predict the pore pressure, including the overpressure zone, which is important to avoid the kick and the blowout. Drilling optimization by analyzing rock properties in situ stress, which help to use the safe mud window used for the drilling. It's very important. Well bore and stability, how to predict this formation is higher or lower, and add casing design or increasing mud weight gradually during the drilling, which is very important. Also, on the reservoir application, its characterized geomechanic provide information on the mechanical properties of the rock, such as porosity, permeability, and strengths. This data help on understanding the behavior of the reservoir. It's very important in hydraulic fracturing techniques using the design fracture propagation, fracture design, fault stability, and the trap integrity, which is very important and assess the stability of the fault. Maybe if this fault is reactivation due to the production or due to the regional tectonics happen on the area or due to the production reactivate the fault, it's very important to monitoring this real time during the production. Also, the compaction and sand production, which is the main problem we face, especially on the offshore drilling, is very important because the facilities of the production from the offshore is very expensive. And this sand during the production, if it's failure after the production, it will be the pressure unstable. This sand will move on the line, make some holes on this line and escape the hydrocarbon. It will make a lot of problem, and also it make a disaster on this assets, which is by million of dollars. Now we start just an example for well bore stability. Well bore stability is a major concern on drilling operation and stability, such as collapse, breakout, washout. It's also non-productive time on the drilling. It cause a lot of problem. The rate of the rig, if you're drilling with semi-sub or drilling ship, it will cost everyone of them to save this issue. It take time, take money. You should mitigate this failure by analyzing stresses before drilling and also to estimate the pore pressure and real-time update during the drilling. It's very important. Also to define the safe mud window and also to deal with the hazards that you didn't see before the drilling. It's very important to update step by step to monitoring the caving, monitoring the type of the caving, if it's due to pressure or mechanical problem or washout, or the pore pressure is lower than your reservoir pressure. Let's see each one of them and focus on it time by time to save money and save a disaster having maybe on the drilling. The well bore stability analysis and mud weight window. Mud weight Choosing the safe mud weight is a big challenge because define the safe range of the drilling fluid density to maintain well bore stability. The lower limit prevent collapse, while the upper limit avoid fracture of the formation. The correct balance ensures that the bore hole remain intact with inducing losses. Geomechanics modeling of pore pressure, collapse pressure, and the fracture gradient enable engineers to set this window correctly, optimizing drilling safety and efficiency. The best safe mud weight used window is you are higher than the pore pressure, lower than the SH minimum. Because if you lower than the pore pressure, you will get some kick. If you are higher pore pressure by number exceeds the SH minimum, fracture will start to appear on your reservoir. After that, you will get a losses. If you still like that, you will get a complete loss. Now you exceed the SH minimum by a higher number, so it's mandatory to monitoring all this one and just to use the safe mud window correctly. This is what we're talking about. This is the bore pressure, the wheel bore cross section also. It's high volume of caving while flowing, which means the mud weight you use is lower than the bore pressure. In this case, it will be unstable. This caving will going to down on the hole, maybe cause stuck pipe. It is very critical. If you drill between the pore pressure and the breakout limit, now you will get low volume of caving because you are higher than the pore pressure, but less need still need some weight to control your formation. Stable wind is the green one between the breakout, or we can take it on the predict software like shale failure analysis. It's especially for the shale. Because if you drill between breakout and SH minimum, this is a stable window. You will not exceed and making fracture of the formation, and you will not get any kickoff. If you exceed the SH minimum by low number, in this case, the fluid will loses a natural fracture of the formation. You will get some some losses, partial losses. If you exceed the fracture pressure nearing to SV, now all the fluid loss and induced fracture will happen, and you will lose all your mud weight, mud used in the well. Why will pore stability analysis is important? This is showing the casing collapse pressure, burst, casing collapse. This is what happened on the casing of the well. This is real. Well pore stability directly influence casing design and mud program, over planning, proper estimation of the pore pressure and fracture gradient prevents this catastrophic failure, like blowout, stuck pipe, and well design. Geomechanical problem ensure casing integrity. Also, if you're drilling like the Gulf of Suez, we have an active salt. This salt, you need a casing grading is higher because if you're using a low grade, the salt is movable, especially in the southern part of the Gulf. In this case, the salt move, the casing collapse, and we also have a many cases dealing with this one. You use low grade, didn't estimate that the salt is moved and the stress is very high. You should use a casing with a high grade. It's more expensive, but it's more safe to lose the well. I know one company is using low grade well to just customize the coast. And after they drill, we found some layer was more than 10,000 barrel of the test. And after we going for the casing and we put it in the production, we cannot entering the well because the whole hole is collapsed from South Gharib, the salt of the Gulf of Suez, and we lose the well. This is just a small problem. Not cost optimization is variable in everything. You should know the stresses, you should know the problem. After that, you choose the proper way to deal with it. Another example, this is from Iran. This is a national company drilling. The rig is blew out. Poor pressure is estimated is fundamental for the input fuel design. It's in fact that the well, after the drilling, they face low mud weight. The rig is open It's a blowout, and the rig number, I think number 147, it's completely destroyed. The reason for that, the rig is completely destroyed and some workers were killed. After the effort extinguished this fire, it's still for 58 days just to save this fire. It's a great disaster on Sylphed oil field. This is no the case study on the paper based for it in Iran and caused a great disaster. This is a problem in the well design and wrong estimation of the pump pressure. Hydraulic fracture principle. Hydraulic fracture create artificial fracture in low permeability formation. We have formation like limestone or shale. It's the source and the reservoir at the same time, but with a very low permeability. In this case, we called it unconventional. We need to enhance the flow capacity and to increase the productivity of this one. The process involved injection fluid at high pressure to exceed the minimum principal stress because it is the less stress we can propagate on it. It is the least one in value, causing the rock to fracture. Geomechanics define fracture orientation, cross direction, and contaminated. Understanding this parameter help engineers to design fracture treatment that maximize productivity. Also, it's important to use the proper fluid for each formation because in case something like shale, and this shale is montmorillonite, if this shale, if you use the water, in this case, the shale swing this water and for now all damage of the reservoir. So using proper fluid like acid, water, oil, or something like foam, it's most important using the best proband. Proband the idea of the hydraulic fracture is making fracture wider as you can, and after that, prober after the fluid, you go to the proband, using proband just to save this fracture you open from the frac open. Use it ceramics and choose some parameter that not make a skin in the reservoir to just make it open and start production from this unconventional resources. So it's very important to know, it's very important to use just a suitable one. Which one of them you should make a good model, good 1D mechanical earth model, because it control if this will be propagated or not. Hydraulic fracture design. A successful fracture required integration, mechanical stress, rock properties, and the natural fracture network. Accurate modeling allowed to predict the fracture height and width, as we discussed, propagation direction, stress, such as shale layer can limit fracture growth because it is more ductile. We will discuss in detail. The best one to use it in the frac is the brittle formation. We have brittle and ductile, more brittle. We focus in this area, more ductile. I think we will not go through this layer. Or we can just think on a formation for the layer with a high brittle. It's better and the best candidate for the hydraulic frac. For the sand production, it's a great problem. Occur when the formation fail mechanically and loose grains flow into the well bore. Due to the production, the pressure around the well is decreased. Now sand start to move, especially in some interval or some reservoir like in Mediterranean or Nile Delta, where the sand or reservoir is mainly sand and this sand is loose. It's not cemented by any cement, not argillaceous, not calcareous. In this case, this make him the best candidate for on the production. It will lead to this sand is move with a high pressure. This is common issue in unconsolidated reservoir, as I said, especially as example from the Nile Delta or Mediterranean. It's weakly cemented formation. The problem lead to erosion, blockage, and reduce productivity. It will lock the formation, no produce, high sand production. It will affect our facilities. In some facilities, it cannot be closed because it's like Mediterranean or Nile Delta. You use many platform and Just collect all of this production in one platform. If you close this one, you will lose all your production. So it's important to monitor it and to use. Maybe the decision of the gravel bag is the best solution for this one, but the gravel bag is very expensive. I think it's until at the last number I updated from our reservoir from 3 years, it's $1 million. Yes, it's expensive, but if you need it, you should use it. Unless you will lose your production, close platform, and save your line. Also, how to manage this product, the sand production, involve predictive modeling. From the beginning, we run 1D mechanical earth model to see if the sand in the future, after simulation and the production, it will be a problem for us to this going to the well bore and to the line or not. It's very important to predict this one just to save money and also to save your production. Geomechanics model help to determine safe operation. Envelope control techniques like gravel backing, as we said before, fracking backing, or chemical consolidation can select based on the formation strength, production objective. Rate measurements is another key tool, producing below the critical row down. In this case, pressure reduce sand risk while maintaining economic flow rate. You should decrease the choke size and monitoring the production with less than your capability to produce, just to save your well. A real-time, real-world case study. This is first. This is geomechanical drilling operation. And geomechanical drilling optimization, and its use in casing design, lost circulation, and stick pipe prevention. Our model will save all this problem. That's also effective geomechanic planning will monitoring reduce the NPT, non-productive time, and the overall drilling cost, enhancing operation safety and emergency. It's very important to know that, and very important to get a good model for your case. Each one is different. Just very quick, we will real world case study. We just use two case study. First one is conventional reservoir, and second one for unconventional reservoir. For conventional reservoir, it's well bore and stability problem. In this deep water sandstone reservoir, well bore and stability was a major challenge. Overpressure zone we found and the high angle contribute the instability and non-productive time. Geomechanical analysis revealed that anisotropic stress and weak bedding plane control the failure pattern. By refining the stress model and optimizing mud weight, stability was improved and the drilling performance enhanced. The problem is this is a high angle well, and this is normal regime. In case of using a high angle, in this case, you are cutting the SV because in normal regime, vertical stress is sigma 1. This is vertical. You're drilling just perpendicular to the highest stress on the area. You will get an issue for the poor pressure of the formation and also the above stress is SV on you. So, in the normal stress, always avoid the high angle wells because the most high angle in normal regime, you will face the poor pressure and the pressure of the SCV, which is the sigma 1, the maximum stress of the area. So traditional with poor stability, we done geomechanical analysis as trough formation, stress distribution around the well pore, just in situ stress, and have the trajectory to impact the well pore and stability. How to solve this one? We use the key of mitigation, the well pore and stability, integrated geomechanical approach, real-time monitoring of the drilling, allowed proactive adjustment. Fluid design optimization minimize shale swelling because also shale in this area is a swell. And drilling with water-based mud is a big mistake to control the shale. So this is optimized, minimize shale swelling, mechanical weakening. Advanced modeling calibrated with core, log data, refine collapse production prediction. This measure reduce non-productive time and enhancement drilling efficiency. This is the case number 2 for the unconventional reservoir, multi-stage hydraulic fracture in shale play. In this shale play, complex fracture network and variable stress contribution pose a challenge for stimulation. The problem is casing deformation in a common fracture operation and well longevity. Complex geology, discontinuous influence, fracture and growth and fluid leak off. Geomechanical challenge also the in situ stress field with a high existing fault can be reactivated by fracture, leading to induced casing deformation. This is the main problem, and fracture complexity stress distribution and reorientation, injection and fracture opening, further completing fracture probe and transport. Understanding this challenge is important for design effective and safe hydraulic fracture treatment in shale play. Microseismic monitoring is important tool to real-time interpretation performance and identifying fault reactivation in shale play. Because after the production, this high magnitude microseismic indicated fault reactivation, which can lead to casing deformation and seismicity. Seismicity or fault reactivation is due to the frac or due to the production as well. It's make a big problem in this case, and the frac is propagated with a high area. Now you will affect the well and the productivity. P-value analysis derived from the Gutenberg assess the relationship between the earthquake magnitude and free value suggests higher proportion of large magnitude event. Optimizing strategy, understanding the relationship, fraction microseismicity, and fault reactivation allow to design and include cluster spacing and the fluid injection rate. Early warning system curve can be warning system of the potential fault reactivation and the casing deformation in proactive mitigation. Now, for the future trend in reservoir geomechanics, all the system we discuss in this webinar is used. Now, for the future, we have advanced tool using this one like machine learning, real-time monitoring that system, and AI. Integration with other disciplines on geomechanics is mandatory because it's increasing the integration with other subservices, contributing the broader digitization of the energy industry and forecasting understanding of the reservoir behavior using all the model advanced and so on. Now in some ways like predict or IB or TechLog, we used a machine learning module. It's added in all of this one just to predict the optimization of the drilling and also to detect the interpretation of complex of geomechanical data. Thank you for your all attention. Thank you for all for your attention. Today we have covered the key principles, measurement techniques, and the application of the reservoir geomechanic across conventional and unconventional reservoir. I hope the session has provide valuable insight into how mechanical understanding supports better reservoir performance, safe operation, and innovation solution for the energy sector. Thank you for you all, and I am here for any question.
Thank you, Dr. Mahmoud. We have sent the attendance form in the Zoom chat. The form will be closed after 5 minutes of the session. So everyone, please fill out the form. If you have any question, you can ask Dr. Mahmoud.
Hello.
Hello?
Sir, am I audible? Hello. Hello.
Hello?
Sir, I have a small doubt regarding the capillary pressure. My doubt is that we will measure the capillary pressure in the laboratory and how we will measure the capillary pressure in the real field scenario.
Calibrate pressure is very important because it is affecting the integrity and how the fluid is within moving inside the reservoir. It's very important. Why? Because its effect on sea information based in modeling on the migration of the fluid. It's affecting on the source rock and also during the reservoir, on the reservoir inside. And also it will affect how, if this capillary pressure affecting the cap integrity. If this is very high, now in this case, the fluid is escape and going uh, from the ceiling of the reservoir. It's important also using the stress integrity for pressure and comparing to the SCV to the capillary pressure is very important because in some cases there is some tectonics not related to, of course, capillary pressure. It's important to solve this issue to estimate a good geomechanical model, include all of this data. Of course, if I have capillary pressure, I will be happy because it solves a lot of issues, not only in geomechanics, it's other stuff, another stuff. So this is right. If I have this information, it will also affect our model. Agree?
I mean, asking that how we in laboratory we will measure in core sample, but in real field, how we will get the capillary pressure values there? Is there any manual method in which we can measure that one or
Uh,
some other?
best way for the estimating the capillary pressure, I think, is the laboratory. The method is used in this model, I think, in some software like Trinity. You add a lot of input, but actually I didn't trust this estimation. If you want to get best capillary pressure for your estimation, take it from laboratory.
I mean, you are saying that we are going to upscale that from core level to the real field, right?
Sorry.
I mean, you are trying to say that it is we are in software we will upscale the laboratory values to the field values.
Yes, of
Okay,
course.
okay, sir. Thank you, sir.
There is a question from Nivad asking about the role of geomechanics in well trajectory, planning and choosing casing setting depths. I think the casing design or casing depths we already discussed in the presentation. Using the well trajectory planning, yes, it's very important as we discussed just in normal fault regime. It's important to avoid the high angle because in case of the high angle, you will face the poor pressure and also the SV. In normal regime, the vertical stress is bigger than SH maximum, is higher than SH minimum. So if you use a high angle, prepare yourself to a lot of drilling issue because you face not only the poor pressure but also the SV. In this case, based on our presentation, you should use the safe mud window at the end or just near to SH minimum because to avoid any kick or any problem during the drilling, because if you control during the drilling and the circulation of the well, but during the stability or connection or something like that, you will get some connection gases, because if you just near or higher by value of poor pressure, you will face this issue. So if you start, in some cases you are forced for that. In case of you drilling on normal like Nile Delta or Western Desert on normal regime, but you drink from platform. So I am forced to use a high angle because I drill from platform. In this case, you should estimate your model and after that exceed your estimation by value just near from SH minimum to cover this problem you will face during drilling this well. Another question from the mechanic essential for optimizing field development and ensuring good bore stability, production and injection operation. Yes, it's very important to know the stress, and if you produce from this formation, the injection you will use in this well is depending not on the original stress, but on the stress after the production. It is mandatory to use it because it will affect the injection pressure. Because in some well, and also using infill well is depending on this. This is good. This is actually masked, Ibrahim. That's a very good question because it will affect not only in the producing well, but also in the child well that we called infill well. If used for the production or for injection, you may be during the production for if you drill from the well with a high rate and this stress is decrease dramatically. If you now inject or just frag this zone, the high stress will going directly not to the produced zone, will going directly to the less stress SH minimum. So you will going exactly to the water zone and you will lose the production well and the injection well or the infill well as well. So yes, it's mandatory the well pore stability and during your model you should use the accurate and the most real data, not the old one because the stress is changed with the production or something like that. And we will add case. Sorry, I don't. Yes, I forget to add it in the webinar. Pore pressure for the same well before production and after the production. The well before the production is an overpressure zone due to the RFT is approved this line. And after 3 years of production, after drilling the infill well, we get a high range of water, no hydrocarbon because the parent well, after we get test of the static pressure, we ended up the RFT is lower than the hydrostatic. Of course, it's important. It's important to know, and it's important to update. Another question: the main rock mechanical parameter, Young's modulus Poisson-Nash, and how are they measured? Actually, we have two methods. This is another question. Two methods to estimate the rock mechanics. We have estimated from logs, and this is the what we called it dynamic rock mechanics, and we have static. Static it means it's original. The original cannot be estimated by the logs. It's estimated only on the core from the core on the laboratory. It's very important to use it as a static just for your reference. But the data we used in our model, in the frac, on standard production model, on the infill wells, on something like that, you will use the dynamic. The static is important to know the behavior of your reservoir. Maybe in some reservoir of sand, we will add this one in our workshop. We will add some sand very brittle, used for fracture. Some sand is very ductile. It is the same sand, the same reservoir, by the way, but the stress is totally different. Young's modulus is double the time for this well. Ended up with this is more ductile, more brittle. More ductile, it will not cause a sand production problem, but it will cause a very big problem in fracture or production of this layer. So this is also good question, but we have no method. The second one is dynamic. It's used directly from the sonic and density, especially the shear. You should use it because the shear moduli is depending on the DTS. But for the Poisson ratio and for the other stress, use sonic. Overburden SV, we will use density and something like that. Are going to receive notes, please. Search it account. Okay. So the case depleted reservoir. How manage geomechanic hazard for the next one? Yeah. This is agent. Ask any study case about depleted reservoir and how to manage geomechanical hazard for the next development drilling well. Unfortunately, agent, I added in our workshop, but not in our webinar. Sorry for that, but just for the time of the webinar, it's only 1 hour. So I just focus in only 1 hour. I use one conventional, was unconventional, but your question is very good. It is important because the development plan is dependent on the geomechanics as important rule. Why? Because using the infill well is depending on the stress and the effect of this well is withdraw from your field. If this well as we call it cannot withdraw the hydrocarbon 300 meter, like something like that. So you should put your infill well out of this stress by more than 300 meter. If you added in the same stress magnitude of this well, you will lose both, or you will lose the most produced one, and or in case of stability, you will get the same production from both, and you will lose production from the current well. So it is very critical to know the stresses and to detect the drainage of the well before we add more infill well, because it's mandatory on your plan and the FDP, the development plan for your field. Okay, gents, how to estimate another one? Poor pressure, stress exploration field, don't have any previous data. Yes, this is good question from Nivad. In this case, you have two methods. The best one is using the interval velocity. We have a cube from the interval velocity seismic. We can use a survey of the well, just uh, just proceed well for your well, the same direction, the same survey, extract the interval velocity from the seismic cube, and convert this interval velocity, if you don't have Predict or some advanced software, to the sonic, and after that, make your workflow for the pore pressure and fracture gradient estimation. If you have in your the new concession you awarded from the ministry and you want to use it, maybe you have surrounding well which is near from your well, use a sonic of it. But I don't prefer this one, because some issues you can use it. You can use it in the Western Desert, you can use it in the Gulf of South, but no also Gulf of South, maybe Western Desert only. But another way, if you case about you're talking about some channelized system like in Nile Delta or Mediterranean, or like a complex structure regime like on the Gulf, you have faults in everywhere. So the distribution of the reservoir, or you can detect the reservoir for long distance. In this case, I don't prefer to add this one, because we will discuss some cases drilling two wells with five, it's only 50 meter, I think, 50 meter, and we ended up with different channelized system, and we get kick can cause a very big problem for more than 20 days to control this issue. And the distance between the two wells is only 50 meter. So I didn't prefer to use this data from surrounding or nearby wells. I prefer using the interval velocity. Of course, it will not get the same accuracy or the same data quality like the sonic, but it will be respect the trend and the measure you found on your well, inshallah. How can you use chromatograph coming from mud logging? It is very important, because gas chromatograph, maybe if you're drilling with a pore pressure lower than the reservoir pressure, in this case, your mud weight cannot control the formation. You will get something like connection gases during the stop the circulation and start to connect the drill pipe. In this case, your pore pressure is less in case of static, not in case of dynamic, because the dynamics, the ACD is just the pore pressure is increased during the circulation. The ACD will control if the pore pressure difference and the reservoir pressure is not big. ACD will solve this issue. But in case of static, ACD is neutral. So now pore pressure in front of reservoir pressure, if it is a little bit higher, you will get some connection gases. But if your pore pressure is lower by big number of the reservoir pressure, you will get a kick of gases. Now you will notice in the chromatograph a very high total gas, and you will see a component until 2C5 until your chromatograph can estimate. So this, yes, using the chromatograph for gases from the mud log, it is very important. Also the ROB, It will affect the drilling. It's important to notice all this together. Abandon. Okay. Depleted reservoir and how management geomechanical hazard to the next study. How optimize the well placement and completion strategy considering geomechanics. Soil placement and completion strategy. Yes, this is important. I think we discuss it, but we will complete. How to optimize well placement and completion strategy. Completion is very important for considering the geomechanics because drilling in reservoir sand. This is an example, and also we will put 2 or 3 examples to discuss this point. Saim Ali, this is good question. Yes, it's very important to use it. Also, if an example, I drill well with a sand reservoir. This sand is a normal and the virgin pressure. After the production, how can I predict if this sand during to the decreasing of the pressure due to the production, it will be moved and going to the oil pool or not? Geomechanics model is very important on that because before going to the completion, you should use a gravel bag. This gravel bag is a screen of gravel used on front of your reservoir to prevent the sand is going to the well pour during the production. It is very, very important. I know it is, I don't know exactly right now the price of it, but the last update is $1 million. This is very important. So to add $1 million in your well, to just add a gravel bag, if you do a wrong geomechanical model and no, we will use this because this sand may be produced after the production, you will cost $1 million for nothing. But if the geomechanical model of stimulation for the production through time and decreasing the pressure and predicting the production, after that you will end up with this sand can be production after the decreasing of the pressure, we should completely change the completion design to add gravel back for this well. I know it's cost, but also this cost will save you a lot of problem you can face if you're drilling like in sea or on the offshore. The facilities is very expensive, and also this facilities is all connected to a line. If this line is filled or blocked by the sand, sorry, يعني all this production you will lose. So by adding $1 million, if one have a current price for this one, please tell me. It's mandatory to use it. So all your completion will be totally changed. And the strategy also as well, if I have another formation to start with it, using this one, it's okay. So this is good question, and we will add it in our workshop, by the way. Casing due to fault. Casing deformation due to fault. I need more information. How can I get sample data of the reservoir and the bore pressure to my project? It is an open resource where to can find them. معيش. This is you can need this data. I think there is some site. Uh, I don't remember the name. They offer some seismic and some well as demo used to your you can use it on your project. It's legal, it's published, and use it for the scientific purpose. I don't know, I don't remember just the site, but I can share it with you, or I can share with engineer Amr and send it to you. It's okay. But it's available. Some wells is available. Some seismic is available. You can use it and estimate this practical and use it on your project. This is normal, and by the way, it's legal. The best software to use, we have IB, TechLock, Predict. If you ask me, the most easy one is IB. It is very fast. After that, TechLock, the best one, but it will take a lot of time on calibration, the Predict. But It is the best software, and also it is the only one that can proceed with the 3D geomechanical model, because it's except a cube seismic, except we can entering the cube of interval velocity or cube of sonic from the inversion, and you estimate a 3D geomechanical model for all your area by your seismic, and at any time you at the well extract exactly the boot pressure and the fracture gradient. You don't need anything. This model is calibrated by the wells you added and most updated with well by well. It is excellent. You can only just 1 minute to get the boot pressure and the fracture for it. Okay. Sorry, during I explained the webinar, I didn't see the chat. So I will answer all the questions. What is our new challenge right now in the mechanic domain? A lot of challenge. Geomechanics, it's not only using the logs, but you use all the available data because geomechanics now is entered in all studies, reservoir, geology, geoscientist, and the basin modeling. It will affect from the 3D basin modeling for the source rock evaluation, and also it will affect the pressure estimation for the source rock. It's very important to see how this source is yielding oil and the quantity of it, and if this is stress capable to produce this or not. It's very important from the exploration phase, during the production phase or reservoir, or the infill well development plan. Of course, we have every stage have their challenge. In the exploration, you have a challenge of leak of data, less information, no wells maybe. On the exploration, on the production or the drilling, actually, you maybe face some layer you didn't added on your estimation. On the production, the effect of the decreasing the pressure will affect the stress, and by the way, it will affect the SH minimum as well. So if you frack a well from the reservoir or development stage, you should know exactly this H minimum, because maybe you use a pressure which is exceed by the very big number. Now the water is coming too fast. So this is a lot of a challenge in the reservoir stage. Also in the production stage, as we mentioned, some the production or the affecting of the infill well you added to the another well. It's very important to notice all of this. All of this is a challenge. Any wrong interpretation will lead you to a wrong decision. Another question. If Y didn't have leak of test data, can I another input to overcome this limitation to estimate geomechanical parts? Leak of test is very important to not in the pore pressure. It will affect directly to the fracture pressure or SH minimum. Why? Because the leak of test, as it's a theory, actually, I didn't add it in the presentation, but I can share it. If I add stress and strain, stress on X, strain on Y, increasing the stress, you will go into the material of the rock in the elastic mode. Elastic mode, we have elastic and the plastic. Elastic mode, the rock is can maintain the stress on it without any deformation. After we're going to start to change the rock shape, now you start on ductile. Start to stress is higher than on the rock. Can it handle it very well? There is a change of the rock, but no brittle, no fracture happen. After you increase stress through time, we will discuss this in detail on our workshop, gents. So it will be discussed. After that, to increase the pressure to the high strength, you will go to the brittle. Now the rock cannot handle this one. At this point, before going to the break or going to the failure, this is the value of the SH minimum. The start of the changing of it is SH minimum. Now, after decreasing the pressure and changing the material of the strain, and the rock start to be brittle, now it is this, we can explain it as extended leak of test. Now you break the formation, so you now exactly know the SH minimum value. Leak of test is good in fracture interpretation for the geomechanical model, but you should your fracture higher than the leak of test normal. It's in the same or a little bit the fracture will be higher. But if you have extended leak of test at the point exactly at the line of the fracture, because this is 100% the same value of it. Maybe you can't edit this on from the core or the laboratory test, but also you can get it from the well before you ending. After you ending the well section and start a new one, you drill 10 feet and start FIT or leak of test or extended leak of test. No one of the engineer or of the company man need to do extended leak of test because you break the formation. In this case, he just searched for the save, not on your getting the proper data. So use leak of test, and this is an indication to your fracture. If you don't have leak of test, just use the trend from the normal compaction trend. Using the normal compaction trend from your data to calibrate the data you have from velocity or from the sonic and extend the shale zone, which has the more risk, or the sand zone on case of the production, not of the version, because in the version, the pressure of the sand will be the same as shale. So it's no problem. For the fracture, you should add the normal compaction trend with the best way on your data to respect every piece of information of your reservoir just to estimate accurate fracture gradient, because if you change the trend, you will change the fracture gradient. We will discuss also in the workshop how to use the normal compaction trend NCT and how to estimate it with the best way in case if you don't have any data. Okay, this is the last question on the chat.
Okay, could you show us the agenda about the workshop, please?
Engineer عمرو.
We will send you the content of the workshop on WhatsApp, inshallah.
Okay, thank you very much. I want to ask you if there any software we can learn in this workshop, like Betrel or Toclog or another software. Thank you very much.
Yes, we have IB software. It uses it's more easy. We will add it on this in this workshop, inshallah. Uh, we can explain this, and also we can just a quick review and take a look if they need. But we prepare the slide of the workshop to the IB. But by the way, we will share that all the software IB, take log, predict the workflow and how you do it. If we didn't discuss this one in only one software in our workshop, we will edit another videos or another something interpreted the workflow. And in case if you need any help with another software due to the workshop, I will be happy to hear from you.
Assalamu alaikum, ya Doctor. Thank you very much for the wonderful presentation.
Thank you, Hamdallah.
Please, if I could ask, I missed the response to the question on depleted reservoir. Supposing like one has is asked to calculate the pore pressure from a depleted reservoir, and the reservoir is not overpressured. Can we just adopt from the hydrostatic pressure, or we still need to do the analysis from the seismic and the well logs?
Okay,
Thank you.
okay, Abdullah. Okay. For the depletion reservoir, we have now logs. We can estimate correctly with the high phase. Actually, the difference between the sonic velocity and the velocity and the interval velocity and the sonic is the vertical resolution of each one. On the velocity, interval velocity, the vertical is not high. يعني هو 100 feet or 500 feet, 30 feet is big high. For the sonic, it's 1 or 1 to 3 feet. It's good to for calibration. For the depletion reservoir, we have already RFT and MDT data, pressure analysis, and the pressure from the production. If you have RFT, it is very normal. Now you estimate the pore pressure originally and calibrate this pore pressure currently. Of course, you don't have a new data. If you have a new well, it is better. It's better and very good. You will get this RFT point or MDT and calibrate back your pressure to it. The static pressure is the same. We always use 0.04. It is identical for the water. It is for the hydrostatic pressure. Now, if your pore pressure exceed this number, so you are good. It's a good number. But if you due to the depletion going back less than the hydrostatic, in this case, you should take all your precaution during the drilling. If you don't have RFT or MDT to calibrate your model, what can we do? We can take from the production, of course, if you don't have RFT or MDT due to the problem in the well, or I cannot run RFT or MDT. Let's go to our colleague in production and reservoir to estimate the current pressure by static point. You can close well, just their techniques to use the production, estimate the volume of the production. It's already estimated. Now, how this production affect on the current of the normal pressure or the original pressure you estimate, sorry. After that, he will reach it up. The static now, we just give an example on the the version, the pressure is 4,000 psi. After 2 years of production, it is depleted. The static from our reservoir colleagues say us, gents, now the reservoir pressure is 2,000 psi, 2,005 psi. The pressure is changed, the depth is the same, the reservoir is the same. Now we use this 2005 psi as a current pressure, converted it to the pore pressure and estimate your gradient. It's an equation. We will add it also on our workshop and how to convert and estimate it. In this case, you add your point on the reservoir based on the current situation. After that, you force it to retrieve your pore pressure to this point, because this is what currently you will face during the drilling. Not the original one you estimate from logs. I know you will get the sonic logs and sonic data. It is good. It will be added يعني very well, right? But you neglect the production. The production will affect the pressure. So if you affect the pressure, you will affect the pore pressure and you will affect the fracture gradient as well. In this case, all or both of these curves will return back to below. I think below the hydrostatic at this level. Let me search for something I can show it to you. It is exactly explain uh, your question. Just 1 minute.
Yeah, thank you, Doctor.
Okay.
Just see where
Yeah, sorry, Abdullah, I didn't find it right now. I can, you can send to Amra, and I will send you just slide explain how this is worked, and with a real case study from Gulf of Suez. I will share it with you. Sorry, I just didn't find the paper because it's on another laptop. I will share it with you, and I will send it to you.
Okay, thank you very much.
Yeah, sorry for that.
No worries.
Okay,
So that's it. Yeah.
sorry.
Good evening, sir. Thank you very much for this opportunity for this presentation also. Uh, I don't know, is it possible to share your screen because I cannot see the screen at all? And is it possible to have the presentation? Yeah, thank you.
Sorry, you have a problem in on the image. It's okay. I can share it with Amr and can send it to you.
Come again?
Okay, I can share it with Amr from Reservoir Solution, and he can share it with you if you didn't see it.
Okay, okay, thank you.
Also me, I can't see the screen of presentation. Is there any problem? You can tell us about maybe Zoom
Look,
Zoom
okay,
technique.
okay, Engineer Ali. Okay, so any other question? Murad asked a question. What we should consider on the scope of work for geomechanics study for oil field? Yeah, you should consider a lot of issues on during this scope of work. You should consider the logs used for the geomechanics. First of all, if your reservoir is sand and you want to make sand production or some issues for that, we should run sonic.bhc. يعني the original sonic, which is only the compressional, which will not help you with this model at all, because you will lose all the shear model. You will get it shear delta TS, the shear sonic, which is used in rock mechanical interpretation. You will use it in the 1D model, and you will use it in the 2D and 3D as well. Also, it is very important in correctly estimate the rock mechanical properties in case we don't have code, we don't have laboratory test. It's important to run. It's not expensive, but it will be good to use it, because if you didn't use shear, you will lose all this information. Another issue for the image. Running the image is important in case of tight reservoir and in case of unconventional, because it is very important in determining stress, and it is the best tool used to estimate the stress magnitude and direction. The best way. Also, you can use a direction by sonic vision or dipole sonic, because it's have direction, but it's not the best like the image. So in case of your reservoir is unconventional, I think image is mandatory. All this point you should consider in your geomechanical study, because you know your field. Of course, scope of work is not the same for all fields. It's different, because each one have their scope due to your production. If I produce from sand, if I produce from limestone, if I produce from normal regime, if I produce from stress like reverse or strike slip regime, each one needs their scope, each one needs their data. If I drill with no problem for sand production, with no problem for unconventional resources, if I have low resistivity base, in case of low resistivity base sand, like something like that, if you don't have image, you will not see it at all. So the scope of work and depend on the information coming from your field. Of course, it is different. Of course, it will be different in each one, and in each field have their story. Okay. Any other question? Okay. If there is no any other question, so the floor is for you, Mr. Amr.